come back to this problem. Elementary reaction. So what is the rate of A? Rate of consumption, so it's R1, not minus 1, minus R negative 1. So some of you guys missed this on the test too. You guys forgot that reversible reactions, we have to include the reverse rate. So I can substitute in, you get K, concentration of A. Reverse rate constant, concentration of B. Right? And you can actually rearrange this, and this is how the book often writes these, as the forward rate constant times concentration of A minus concentration of B divided by the equilibrium constant. And that's valid because so often the book will just jump straight to here. For a reversible reaction, this is where they start. And that's fine. You don't have to start earlier than that. It's fine if you just want to go straight to there. All right, so that's our rate equation. Now stoichiometry. Concentration is equal to flow over the volumetric flow rate. Is that changing? Why not? Liquid. Not because epsilon is 0, but liquid. Because just because epsilon is 0, you're still going to have, in a gas phase system, you're still going to have changes in the volumetric flow rate because the pressure can be changing, which we can neglect, but the temperature is going to be changing when we're in this part of the course. So we can't make that assumption just because epsilon is 0. All right, so you get Ca naught times 1 minus x. And then okay, and so we combine all of those things. And notice we haven't talked about temperature at all yet, except that we haven't gotten rid of those temperature terms. And I'll remind you and so from the energy balance, we're going to put down this form. Remember, delta Cp is equal to 0. Because it's just an isomerization reaction. We take what we've been given, you end up with this equation. Yes?
So going back to talking about the T naught over T, why in the first example we did today where we were doing the liquid system and CSTR, why didn't we include the T naught over T in the concentration?
Because in that case, the volumetric flow rate that we care about is the volumetric flow rate leaving the reactor, and that's at the reactor temperature. In this case, the temperature is changing along the bed of the reactor. And so the volumetric flow rate is also changing along the bed of the reactor.
So it's CSTR.
Yeah, that's the simple way to put it. All right, so we have our energy balance equation here. And then we have all right, so this is the simplified version, assuming that this doesn't change. And so we put in some numbers. Any questions so far? So we have the equilibrium constant as a function of temperature. We have the temperature of the reactor as a function of conversion. And we also know that at equilibrium, what is the rate? And so we plug that back into that top equation up there. Now I need to make sure that I put a little e, because this is only true, this is only 0 when x is at its equilibrium conversion. So the equilibrium conversion is the rate constant divided by 1 plus the rate constant. And again, what we're going to talk about next time, if I put conversion here and temperature here, what is it from the energy balance? Is it linear, curved? Linear, so we're going to start it here at T0 and draw a straight line. So this is XEB. And now, what does the curve for the equilibrium constant look like?
Curvy.
Curvy, is it increasing or decreasing? So what type of reaction is this, first of all? Exothermic. So for exothermic, does Xe decrease or increase with temperature? Decreases, so you get something that looks like this. So if I start at this inlet temperature, what conversion will I hit if I had an infinitely long reactor? Xe, which is right here, right? So that's the conversion that I stop at. This curve keeps going, of course, but that's irrelevant. I would actually stop right here. So what if I start it here? Will I get a lower or higher conversion? Lower, right? And if I started at a lower temperature, I'll get a higher conversion. Right?
Where did the curve line come from? I want to make sure I'm true.
Yeah, I mean, it's the one we drew earlier. I was looking on the board, but you can get it from this. But of course, that makes it look really simple. Of course, these are also functions of temperature. So you get it from that Van't Hoff equation, essentially. Okay, so let's imagine I have a system where I can't go beneath this temperature. Okay, so this is the minimum temperature at which my reactants are maybe in the gas phase. And my reactor is a gas phase reactor. If I flow liquids, it'll ruin my catalyst. So I have to start here. This is not an option. And my boss tells me I've got to get to 90% conversion. What do I do? Recycle. That's similar to what, yeah. What's something else I can do? Add catalyst isn't going to help me. That just helps me get to this point faster. Equilibrium is not affected by catalyst. Catalysts just make the reaction occur faster.
Something with the mass balance?
No, nothing with the mass balance. Can you use steps? Yes. So that's what you do. It's called interstage heating and cooling. So here's PFR1. And then I come out and I'm here, right? Let's assume that all the PFRs will hit equilibrium. Then what do? Cool it. Maybe to this temperature, because, sorry, I said this was my cutoff temperature. So I stop, I go right back to that same minimum temperature. And then I stick it in another reactor, and where do I go? Come back,